We talked quite a bit about electron configuration in first year chemistry, and in order to understand how electrons are arranged around an atom, we learned that quantum mechanics taught us about a probability distribution, a location where we're likely to find an electron that was described by this complex math of the Schrodinger equation. When you solve the Schrodinger equation, you get a set of numbers that is one solution to that complex math. And then that is a quantum number. Each electron is defined by that unique solution. Each number in a set of quantum numbers essentially defines the probability of finding that electron more and more precisely. So as a metaphor for that, we could imagine you're an office aide trying to find a student to bring them a note from the office. So the first thing you need to know fundamentally is that student at Johnson High School? Do they have early release? Are they at CTEC? So that's the first biggest quantum number, is where in that overall space am I likely to find that electron? Then I would need to know more information than just that. There's a lot of people at Johnson. So I would need to have an idea of where that student is. So let's say I look it up and I say, oh, they're in chemistry class. So that tells me that they're likely to be in the E wing or F wing, not over in the A wing or not down in the band hall. But even if you know that they're in chemistry class, that's still not enough to specifically locate one student. You need one more level of information. You need to know exactly which classroom they're in. Because if they're in a chemistry class, they could be in Mr. Moore's room or my room. They could be in a lot of different places. So each level of our quantum numbers basically gives us more and more information that we can use to locate one particular electron, because each electron has a unique solution. Because we build on models, we knew that the Bohr model told us that there were specific energy levels. And so we divide those as a shell. That was from our principal quantum number, n. So if you think about how you learned about orbitals and shells back in first year, the very first thing was we had to know what shell we were in, 1, 2, 3, 4. Each shell was then further divided by the angular quantum number into subshells. And that's the S, P, D, F. So you can have, say, 2s or 2p, or you could have 4s, 4p, 4d, 4f. Those are the subshells, like the type of orbital. And then subshells have one or more individual orbital inside them. So this should be a familiar looking chart from first year. We have the S subshell. There's one possible orbital. It's on every level, 1s, 2s going on. And you can have 2 total electrons in an s orbital. Then we have p orbitals, which come in on principal quantum number 2. You can have 2s and 2p. Each set of p subshells are divided into 3 individual orbitals. So it's like having a hallway that's got 3 individual classrooms on it. And you can fit 2 electrons per orbital, so you would have a maximum of 6. Then as you go up to a next principal quantum number, when you get up to 3, now you have the possibility of S, P, and D. And now the D hallway has 5 individual classrooms in it, 5 individual orbitals. 2 electrons per orbital means I have a maximum of 10. And then we have Fs, which are 7 possible orbitals. 7 times 2 would give us 14. That's that block of elements that's offset at the bottom of your periodic table. So just going into a little more detail on this, 1 s orbital for every level. It's a spherical shape. That's actually not why it's called an s orbital. It's from spectroscopy, but S for sphere will work to remember. Each s orbital holds 2 electrons. So there's one of these on every level, 1s, 2s, 3s, 4s, all the way up to 7. P orbitals then are available when the principal quantum number is greater than or equal to 2, 2, 3, 4. There are 3 of these, and they are in fact at 90-degree angles to each other. They are orthogonal. They go along the x, y, and z axis. So we call them the px, py, and pz. Each orbital can hold 2 electrons. And there's a reason why it's 2 and only 2. Of course, 2 times 3 would give us 6. That's why we have 6 maximum electrons in the p orbitals. Now, when we start getting into d orbitals, these energy levels start getting to be very complex looking probability spaces. So we really don't draw them as much. There are 5 d orbitals. You start and you have n equals 3, 4, 5, so there's no such thing as a 1d or 2d orbital. There are 5 of them. They kind of look like 4-leaf clovers. They either are along the axes, that's this bottom one here, or in between different axes, except for this weird looking, looks like a double baby pacifier guy here. But fundamentally, we're not as worried about the shape. We're worried about the type, or the number of orbitals, and the fact that each one can hold 2 electrons. And if you really want to get wacky looking, you go up to the F sublevel. F sublevel has 7 F orbitals. These only start when you have n equals 4 or 5 or 6. That's that offset row that kind of starts in the D block in the transition metals, but since that would make the table really hard to print on one page, it gets offset. Again, 7 times 2, maximum of 2 electrons per orbital. So we have 14 possible F electrons in these 7 F orbitals. So these electron configuration rules are important that we know. The Aufbau principle, electrons are lazy, lowest energy orbital first. This is where we have some difficulties because of the overlap of energies between some different orbitals. We're trying to get to the lowest energy atom. The Pauli exclusion principle is that principle that every electron must have a unique quantum number, at most 2 per orbital. 1 up, 1 down. That's the spin quantum number. It's not really spinning, but it's a way to think about this weird quantum effect. Hund's rule is our last electron configuration rule. And this is the one where we're trying to actually minimize the repulsion between all negative electrons. Like charges repel each other. So if I have a set like the d orbitals, we aren't going to pair them up until we have to. Each one of these equal energy degenerate orbitals get 1 electron each, and then we start to pair them up. So you get 1, 2, 3, 4, 5, 6, and that would give us our full set. So we need to distinguish between 2 different things, writing electron configurations and drawing orbital diagrams. When we write our electron configurations, this should look very familiar from first year. The first part of each subset here, each piece of my configuration, is that principal quantum number, the shell. The second part is the type of subshell. The third part is the number of electrons in each subshell as a superscript. It looks like an exponent. Do not write it as a subscript like a chemical formula or out right next to it. That looks weird. It is an exponent, and yes, that's actually important enough to lose points on the AP exam. So if you remember the pattern that we did in first year, you have that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Remember that weird little gap here where we have these 4s electrons that fill before the 3ds, because as I always say, nature does what nature does, and it didn't ask me what would make my life easier. Now, drawing an orbital diagram, each box in each picture, because a diagram is a picture, each box represents an orbital, which must be labeled. You can't just draw boxes and not have any orbital configurations next to them. Electrons are shown then as a up or down one-sided arrow. For example, since there are 3 p orbitals, you would have 3 identical boxes for that level, kind of like we saw on the last slide with Hund's rule. All the other rules apply. The real point of an orbital diagram is it's really helpful for finding where I have unpaired electrons in a configuration, which is going to be important in describing some of the macroscopic properties, or determining the likely charge on an ion, whether it's easier to remove or to fill empty spots in an electron configuration. Of course, remembering that octet rule that we learned in first year. So here is the basic, all the way up for everything you would need on the periodic table, orbital diagram. And as we start to put electrons into it, we have to remember we fill the lowest energy orbital first. So the first thing I would do is I would fill 2 electrons in the 1s. That would give me the electron configuration for helium, 1s2. Then I would start putting electrons into the 2s. So I would put 1 up, 1 down until that was full. 2s1 is lithium, 2s2 is beryllium. Then the next highest energy level is the 2p. Those fill according to Hund's rule. 1, 2, 3, 4, 5, 6. Now I have 2p6. Now I look for where the next electron is. That's sodium over on the third row in the S block. So I would fill up sodium and magnesium. I follow across. I'm back in the P block with aluminum. Those are going to fill 1, 2, 3, 4, 5, 6. And I really do suggest being in the muscle memory of always doing it 1, 2, 3, 4, 5, 6, because it really helps keep you from accidentally violating Hund's rule. Once I finish up with argon, then I'm looking for the next electron, element number 19. And we see that that is black in the S block of the periodic table on the fourth row. So 4s is going to have electrons in there as a final state before the 3d. So we'll fill up calcium, potassium, and then calcium. And then we go into that transition metal D block. That has my 5 degenerate orbitals here. And so I would end up filling them according to Hund's rule, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I would go on to the 4p. After I finish 4p, I go to 5s, then 4d, then 5p. So we just keep following that pattern as we go. So there's our basics on doing electron configurations. You'll get some practice with that in class, and hopefully should be a quick one since we did learn it in first year.